Good day, viewers all over the world. Today we want to look at the second order linear homogeneous differential equation with constant coefficients. Second order linear homogeneous differential equations with constant coefficients. That is, I will be starting with the characteristics equation. So the corresponding second order linear homogeneous differential equation is given as this. Please, let's look at this equation 1. You realize that y prime prime is second order. So these are the typical example of second order differential equations. But in this case, it's homogeneous. Why is it homogeneous? Because the right hand side is equal to 0. We can also have second order linear non-homogeneous differential equations. In that case, the right hand side will not be 0. The right hand side can be a function, can be any function, maybe this equal to sine x or 2x squared plus 3x. Once the right hand side is not equal to 0, then that second order is non-homogeneous. Then in this case also, a1 and a0 are constants, they are not variable. We can also have second order linear non-homogeneous differential equation with variable coefficients. If it is with variable coefficients, then this method of resolution will not be applicable. But what we are trying to consider in this video is the second order linear homogeneous differential equation with constant coefficients. We know the meaning of homogeneous now. The right hand side must be equal to 0. Then constant coefficients simply means what you have beside y prime and y must be constant. A1 and a0 must be constant. So in which a1 and a0 are constants is, if you want to solve this second order linear homogeneous differential equation, we are going to write what is called the algebraic equation from the differential equations. That is, the algebraic equation is obtained by obtaining from 1 by replacing y prime will be replaced by m squared, y prime prime will be replaced by m squared, y prime will be replaced by m, then y will be replaced by m0, and m0 is equal to 1. So if I give you the differential equation, what to solve second order homogeneous differential equations, try as much as possible to write the algebraic equation, which is actually going to give us the characteristics equation. Then once we are able to do that, we go ahead and find and solve the characteristics equation. And of course, this is the characteristics equation. This one can be factored into, of course, when you have something like this, it's a form of quadratic equation. Then if this is quadratic equation, we know what to do when we have quadratic equation. Now we use completely the square method, formula method, or we use we factorize. We can actually factorize it. So if you want to solve second order linear homogeneous differential equations, rewrite the differential equations in form of algebraic equation, which is called the characteristic equation. Then try and solve it. Once we solve it, then we know what to do. So the characteristic equation can be factored into what is called 3 here. Then how do we now solve the problem? From this 3 down, what do we do? From 3, this 3, in which the characteristic equation has been factored, what do? We go ahead and find, once we are able to get the value of m1 and m2, then we go ahead and find the general solution. But because this is an homogeneous equation, the complementary solution will represent the general solution because the right hand side is 0. But admittedly, this is non-homogeneous equation. After finding the complementary solution, we go ahead and find the particular integral. So the general solution will be addition of particular integral and complementary solution. So once we are able to get the value of m1 and m2 here, then we find we go ahead and find what is called the general solution. The general solution. So how do we find the general solution? How do we find the general solution? The general solution of 1, that is the differential equation, is obtained directly from the roots. Yeah, in this case now, like what you have here now, m minus 1 into bracket m minus 2 equal to 0. It simply means that m is equal to m1 or m is equal to m2. So m is equal to m1 or m2. m1 and m2 will represent the root of the characteristics equation. So the general solution of equation 1 is obtained directly from the roots of the characteristics equation 3. And the general solution in this case now, from this root now, there are three cases to be considered. There are three cases to be considered. Case one, under the general solution, case one simply means that if M1 and M2, if M1 and M2 are both real, if M1 and M2 are both real and distinct, just like we have it under the quadratic equation, if M1 and M2 are both real and distinct, two linearly dependent solutions are, if M1 and M2 are both real and distinct, two linearly independent solutions are, these are the two linearly independent solutions are E into bracket M1x and E into bracket M2x, and the general solution and the general solution will be y is equal to C1 EM1x plus C2 EM2x. This will be the general solution. That's for case one. Case two. For case one, if M1 and M2 are real and distinct, this will be the general solution. Then case two, if M1 and M2 are real and equal, if M1 and M2 are real and equal, that is, in this case, M1 is equal to M2. If M1 is equal to M2, two linearly independent solutions, in this case now, two linearly independent solutions are, if they are real and equal, the two linearly independent solutions are EM1x and XEM1x. And the general solution is going to give us y is equal to C1 plus, that will be C1 EM1x plus C2 XEM1x. That's what we are going to get here. So that is what we are going to get here. Then if we factorize this, of course, if we factorize this, we are going to get C1 plus C2x into brackets EM1x. That is, under the second condition, we realize that the two solutions, the two roots of that equation are real. They are real and equal. M1, here, M1 is equal to M2. Here, they are distinct. M1 is different from M2. When we find the root of that characteristic equation. But here, M1 is equal to M2. What we are going to do is that the first solution will be EM1x. Then the second one, there will be additional x. We are going to add x to this. That will be XEM1x. So that the general solution will look like this. Then by the time you take out, you take the what is common, we are going to get our y to be equal to C1 plus C2x into bracket EM1x. So that's what we are going to get in the second solution. Then the third solution, just like we have them, we have this under quadratic equation. So when we talk about discriminants under quadratic equation, it's the same thing here. You know, the discriminants, when they are real, they are complex. So in this case now, if M1 and M2 are complex, if they are not real, and if they are not real, if they are complex. So if they are complex number, maybe say M1 is equal to A plus IB, then M2, maybe M2 is equal to A minus IB. Then what will be the general solution? In this case now, if they are real, if they are complex, M1 is given as A plus IB, then M2 is given as A minus IB. So two linearly independent solutions are, the two linearly independent solutions will be exponential into bracket A plus IB x and exponential A minus IB x. This represents the two linearly independent solutions that we are going to get. So that will be the two linearly independent solutions that we are going to get. And of course, the general solution will be y is equal to C1, we can call it C1. The general solution will be C1, C2, they are just constant. The general solution will be C1 exponential A plus IB X plus C2 exponential A minus IB X. This will be the general solution that we are going to have. Okay. This general solution, under when the two roots are complex numbers, we can actually rewrite this, which is algebraically equal to what you have here is equal to y is equal to is the same thing as y is equal to, let's say, C1 is the same thing as y equal to C1 exponential AX cos BX plus C2 exponential AX sine BX. This same thing as this. Is same thing as this. Algebraically, the two are equivalent. So finally, the final answer, the final solution will be y is equal to exponential AX can come out. So we are left with C1. We are left with C1 cos BX plus C2 sine BX. Of course, these are arbitrary constants, C1, C2. At this point, if I try to change this to A, you can also say A, because something must have taken place. Then this is B. They are arbitrary constants. So that at the end of the day, here will be A. These are just arbitrary constants. But for us to be able to know the value of C1, C2, A, and B, we need subsidiary conditions for us to be able to know the value. So this is how to find, to solve second order linear homogeneous differential equations, as we have discussed earlier. Let me just paraphrase before we close the class. The first thing we discussed is that if you have second order linear homogeneous differential equation with constant coefficients, the first thing is that we are going to rewrite the differential equations in form of algebraic equations. And if you are able to rewrite the differential equation in form of algebraic equation, that algebraic equation will be referred to as the characteristics equation or auxiliary equation. So when we reformulate the differential equation back to algebraic equation or auxiliary equation, it will be in form of quadratic equation. Then we go ahead and solve the roots of that equation, the algebraic equation. So the root of the algebraic equation will now determine the solution to the differential equations. There are three cases that we considered. The first case is that if the two roots are real and distinct, they are real and different, there's a particular way we write that. The second one is that if the two roots are real and they are the same, we have seen that. Then the third one is that if the two roots are complex number, say M1 and M2, then this is how we write the solution. This solution is algebraically equivalent to this. Then this will be the final solution. So in our next video, we are going to give example each on these three cases. Thank you.